Well, I think you're going to find over time that most of the applications in electromagnetics, one way or the other, involve charged particles moving in electric fields, or later you'll see charged particles moving in a magnetic field. And so if you're going to be exposed to many problems like that, and you are, let's start slow. Let's deal with charges in constant electric fields. And if you want to deal with a constant electric field, the parallel plate capacitor does a very good job, because each of these two plates, one negative, one positive, each are carrying a total charge of Q. They've got an area of A, a separation of D. And under that situation, there is everywhere inside, in the interior, a constant electric field given by Q divided by epsilon sub O times A. All right, so in this case, we've got an electron that's going to be released from the negative plate. A proton is going to be released from the positive plate, and they're going to rush across simultaneously. The question is, where is the electron in terms of distance from this negative plate when the two cross? And the answer, you can sort of see the answer to first order right off, because the answer lies in the masses of each of these two. So these two masses are numbers that are probably going to get impressed on your mind just by use and reuse, but if not, you might want to try to get them impressed on your mind through memorization. M sub E is 9.109 times 10 to the minus 31 kilograms. M sub P, the proton mass, is 1.67 times 10 to the minus 27 kilograms. So if you note, the electron is much, much lighter than the proton. The ratio of the two masses, I think it's 1833. It's 3 orders of magnitude, almost a factor of 2,000. So what does that mean? So the physics in this case of charged particles moving in constant electric fields is just the same as a point mass falling under the influence of gravity. You'll see in a moment it's exactly the same physics. Each of the charged particles have impressed upon them the same force, but they've got very different accelerations due to the fact that their masses are so different. So we can dispatch this problem pretty quickly, I think. As I said, the kinematics in this situation is really the same as the kinematics of a ball falling. So if we were to write down the distance at any point in time t that the electron finds itself, it's just the initial displacement plus the initial velocity of the electron times time plus 1/2 whatever acceleration the electron is experiencing times time squared. So this number is 0, this number is 0. This just becomes a sub e of t is equal to 1/2. I'm sorry, x sub e of t is equal to 1/2 a sub e t squared. And so if we were to do the same thing for the proton also has no initial velocity. It's got a different acceleration. It does have initial displacement. The proton at any given time finds itself d minus 1/2 a p t squared. So I put a minus sign in to reflect the fact that the proton's moving towards the origin here. The electron is moving away from the origin. So what is it we're trying to do? There is some time, let's call it tau, and at that time, x sub e of tau is equivalent to x sub p of tau. Okay? And again, you can see the answer right off the bat, right? The electron is moving so much faster than the proton. Again, its acceleration is 2,000 times higher. So the electron is going to run right across the gap D before the proton gets out of the gate. Right? The electron is going to go have coffee and watch the proton plod itself along here. So that's the type of answer we're looking for. This answer is going to be very close to d at the end of the day. So what do we do? Again, we've got this formula right here. Let's put both of these formulas. Let's put both of these conditions into these two kinematics formulas, and we're going to find that when t is equal to tau, then let's just call that common distance x is equal to 1/2 a sub e tau squared. And again, when t is equal to tau, the proton is at the point x, d is equal to, or x is equal to d minus 1/2 a sub p tau squared. So what do we have? We've got two equations in the two unknowns, x and tau. So we know that we can solve them, and what we're after, again, is x. We don't care about the time in this case. So, a couple of different ways to solve simultaneous equations, but in this case, since we want x, let's just solve for t, or t squared in this case, or tau squared in this case, and let's substitute it here. So I'm going to take this tau squared and plug it into the second equation, and I'm going to end up with one equation in the unknown x. That's just exactly what we want. So tau squared in this case is 2x all over a sub e. All right. I'm just going to isolate x now, so I'm going to bring this term over to this side. X a sub e is equal to d. If I put this, let me factor out this x, these two twos are going to cancel themselves, and you're going to end up with 1 plus a sub p all over a sub e is equal to d. And so, if that's the case, x is going to be equal to d divided by 1 plus a sub p all over a sub e. Okay? So what did we say the answer was going to be? We're going to see explicitly in just a second that this a sub p is much smaller than a sub e. Therefore, this number is a very small number, much less than 1. Added to 1, the denominator is just slightly over 1, and that makes x is equal to some number very close to 1, and just below 1 times d, just what we expected. So it's left to us now to calculate what a sub p and what a sub e are. This is the electrostatics now. This a sub p by Newton's second law is the common force divided by the mass of the proton. A sub e is the common force divided by the mass of the electron. And this common force is just the in this case, the proton's charge times the electric field. We've given an expression for the electric field there. So here's the proton's charge, here's its mass, here's the electric field, Q all over epsilon sub OA. Likewise down here, E, M sub P, M sub E, Q all over epsilon sub OA. And if I form this ratio AP all over A sub E, you see everything cancels except for the masses. And there's the very small electron mass divided by the relatively much larger proton mass. And all we need to do now is to insert that into this equation, and we'll get x is equal to d divided by 1 plus m sub e all over m sub p. And if you put the numbers in 1 centimeter here, you're going to find that x is equal to, I believe it's 0.99945 centimeters. Okay?